the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students going through dimensions of vector spaces. Not like you're traveling through the dimensions of vector spaces, but instead you're learning about the dimensions of vector spaces. You should have already watched my video or have learned about dimension of a vector space. In this video, we're just going to talk about subspaces of finite dimensional vector spaces. Really, it's a quick theorem with no proof. I'm not going to prove it here. And a quick example, or a somewhat quick example. The theorem that we're going to need is this guy right here. Let H be a subspace of a finite dimensional vector space. Something you should remember is that a finite dimensional vector space is a vector space with a basis containing only a finite number of vectors. So H is a subspace of a finite dimensional vector space. That actually means that H is also finite dimensional, but that's actually part of this theorem. But it should make sense. If it belongs to a vector space that's finite dimensional, then obviously H should also be finite dimensional. But we're not going to prove that here, but it should be somewhat obvious. Any linearly independent set in H can be expanded if necessary to a basis for H. This is essentially a writer on a previous theorem that we learned, which is this guy right here. If a vector space V has a basis B consisting of n vectors, then any set in V containing more than n vectors must be linearly dependent. Well, actually, it's not really a writer to this, but it's very close to it. What we're really trying to do here with all these theorems is to give you a lot of constraints to basically say, hey, if you have a basis for a vector space, adding any vectors to that set will create a linearly dependent set, because every vector in your vector space can be described by that already existent set of basis vectors. Also, if you remove a vector from that set that's currently a basis for your space, it will no longer be a basis for your space. And that gets us back to this guy right here, because if you do have a set of vectors that are linearly independent, but possibly do not span your entire space, well, you can add some vectors in there if you need to create a basis for your space H. And like I said, H will also be finite dimensional. And by the way, the dimension of that subspace of the vector space V will be less than or equal to the dimension of the vector space V. Visually, it kind of looks like this. You have this big old vector space V. And remember, the dimension of that vector space V is just the number of vectors in a basis for this vector space V. So let's just pretend, for example, there is a basis for the vector space V consisting of 5 vectors. Let's just pretend. That means that the dimension of V must be 5. And then I come along and say, well, I'm going to rope up a subspace within V. We're going to call that subspace H. And to build that subspace, just visually you could see you might need only 4 vectors or 3 vectors, basically fewer vectors. You might need fewer vectors to build that subspace H. And if you need fewer vectors, that means the number of vectors in the basis for H is probably 4, 3, 2, 1, something like that. And so the dimension of H could be 4, 3, 2, or 1. However, if H is actually equal to V, so it's a subspace of the vector space V, but it's also actually equal to V, so it's the vector space V itself, well, obviously the dimension of H is going to match the dimension of V, because to build H, I'm going to require the same number of vectors that are required to build V. That is, I need a basis consisting of 5 vectors. So the dimension of H could be all the way up to 5. And that is why the dimension of H, being a subspace of the vector space V, could be less than or possibly equal to the dimension of V. Now, I spend a lot of time talking about the second part of that theorem, but the first part is also somewhat important. Any linearly independent set in H can be expanded if necessary to create a basis for H. And that should make sense because you might say, well, I have this subspace H. Somebody comes in the room and they say, here are two vectors. That'll span H. And you take a look at those two vectors and they create a lot of the vectors in H, but not every vector in H. Maybe they create something like that chunk in H right there, but you need to create the rest of H. Well, those two vectors obviously didn't do it. And by the way, maybe I should redraw V so that it doesn't look like V is equal to H here. So give me a moment. There we go. So V is a larger vector space than H, which is a subspace of V. But again, somebody hands us a couple vectors and they say, this is a basis for H. And we take all linear combinations of those vectors and find out that there are just some vectors in H that are not born of those two vectors. Although those two vectors could be and should be linearly independent since somebody's claiming they are a basis for H. What this theorem is saying is that, well, if they are already linearly independent, we could find yet another vector that would finish shading this set. So somebody comes in and they say, oh, by the way, I forgot to hand you this third vector. But when they do hand you that third vector, it actually creates the rest of this space right here. And that's the whole point of this, is that if you have a couple linearly independent vectors or n linearly independent vectors, but it still doesn't span your space, somebody is allowed to come in with another linearly independent vector that might create an entire basis for your space. Like I said, I'm not going to prove that theorem. Instead, we're just going to move right into an example. Here's the example. Let V and W be both finite dimensional vector spaces. That is, the dimension of V could be some number, let's call it V bar, and the dimension of W could be some other number, again, let's call that W bar. And these dimensions match the number of vectors in a basis for each of those corresponding vector spaces. And I'm not going to write that for W, you just get the point, I hope. We're also going to suppose that we have a transformation from the vector space V to the vector space W, and that transformation is linear. Now, as you know, in mathematics, everything's handed to you for a very specific purpose, so the fact that this is a linear transformation could be very important in this proof. We're going to let H, which is yet another vector space, be a non-zero subspace of V. And remember, subspaces are vector spaces. That's why I said H is a vector space. And let the transformation of H be the set of images of vectors in H. You know, that's just a quick kind of shorthand language. Normally, I would say take a vector X from H, then T of X is obviously the transformation of the vector X, whatever. But we're just shorthanding this and saying, listen, T of capital H is going to be a shorthand for all the images of vectors in H that get transformed by T. Prove that T of H is a subspace of W, and that the dimension of the transformation of H is less than or equal to the dimension of H itself. Now that last part seems kind of awkward, as if that shouldn't be true, or maybe that it's miswritten, right? Because this is a set of all images of all vectors in H, and we're saying the dimension of that space is going to be less than or equal to the dimension of the original space H. Let's write down some important pieces here. The first thing we're going to need to do is to show that T of H is a subspace of W, which is part of what we want to prove, right? That's the very first piece. Show that T of H is a subspace of W. To do that, we'll need to show closure under vector addition and scalar multiplication for any vector in the image of H. A couple other things I want to mention before we begin. First, the transformation is from the vector space V to the vector space W. They didn't really tell us anything other than the fact that those two vector spaces have finite dimension. So again, their bases contain a finite number of vectors. Possibly different numbers, but finite numbers of vectors. We were also told that H is not the zero subspace. That is, it has more than just the zero vector. Remember, all subspaces have the zero vector, but we're specifically stating here that H is a non-zero subspace of V. And that last part, actually, I should mention too. That H is a subset of V, and it's also a subspace of V. So let's go ahead and start with that first highlighted piece. In fact, let me remove all the other highlights so that you can know what I'm talking about here. We're going to prove that T of H is a subspace of W. I'll use black ink for the actual proof. Let W sub 1 and W sub 2 be vectors in the set of images of H under the transformation T. So they're basically in the range of T when you plug in vectors from H. And let C be a scalar from the underlying field. Now, what does that mean? That these two vectors are in the transformation of H. That is, they are images of some vectors from H under the transformation T. Well, that just means there must be a couple vectors in H itself, such that when you plug those vectors into T, they become W1 and W2. And there we have it right there. Again, just to repeat, there must exist vectors V1 and V2 in the the subspace H, such that T of V sub 1 is equal to W sub 1 and T of V sub 2 is equal to W sub 2. Again, because W1 and W2 are images of some vectors from H through the transformation T. Now remember what we want to show. We want to show that T of H is a subspace of W. So we want to make sure that when you add two vectors that are in T of H, that sum is in T of H. And when you have a scalar multiple of a vector in T of H, that resulting vector is also in T of H. The way that we're going to do this is in one fell swoop. We're going to take a scalar multiple of an arbitrary vector that we created from T of H and add that to an arbitrary vector that we created from T of H. This will simultaneously check off the closure under a vector addition and closure under scalar multiplication. Well, we happen to know that can be rewritten as C times, well, W sub 1 is just a transformation of some vector we called V sub 1 in H. And W sub 2 is likewise a transformation of a vector we called V sub 2, again in H. But remember, if T is a linear transformation, we can rewrite this product right here as the transformation of C times V1. Moreover, we could do the same thing with the addition of these two vectors. Since the transformation is linear, T of some vector plus T of some other vector is T of the sum of those two vectors. Now my goal is to show that the sum of CW1 and W2, which are vectors in T of H, is also going to end up in T of H. Remember what T of H is though. T of H is the transformation of every single vector born from H itself. And if you take a look at this result right here, well, C times V1 plus V2, I'm going to guarantee you is an H. Why? Well, since H is a vector space and V1 and V2 are in H, then any constant multiple of one of those vectors plus the other vector has to be an H because, well, H is a vector space. It's closed under vector addition and scalar multiplication. Since this vector is in H, then T of that vector is in T of H. Now again, just to showcase where we're driving this argument, we want to show that T of H is a subspace of W. We're trying to show closure under scalar multiplication and vector addition. So we took a couple vectors from T of H and we added them up with a scalar multiple. And we arrived at this statement right here, and we're trying to showcase that that statement is actually in T of H. But guess what we've just said? That statement is actually in T of H. So I've taken the sum of two vectors and a scalar multiple of a vector from T of H, and the result is in T of H. That implies C times W1 plus W2 is in T of H, and therefore T of H is a subspace of W. All right, not too bad. Now, what else did we have to do in this problem? We've actually checked off that first piece, that T of H is a subspace of W. Now we need to show that the dimension of T of H must be less than or possibly equal to the dimension of H itself, which is sort of counterintuitive, but I promise it's true. Let me write that down. We want to show, that's what WTS means, we want to show that the dimension of T of H is less than or equal to the dimension of H. We're going to use some of our blue ink above. We know that H is not the zero subspace, and we know that it's finite dimensional. That was actually given up above because it's a subspace of V, and we have a theorem that if H is a subspace of a finite dimensional vector space V, then the dimension of H is less than or equal to the dimension of V. Since H is a subspace of V and V is finite dimensional, H must be finite dimensional. Technically, I didn't need the non-zero in there for that part of the argument, but I have it there just in case. So let a basis for our subspace H be this given set of vectors. So we're assuming that H has dimension P. And that's not a bad assumption. The reality is we know that H is finite dimensional, so it has to have some certain number of basis vectors. I'm just saying that that is P. Let's take a vector from our subspace H here. Any vector within that subspace can be written as a linear combination of the basis vectors of that subspace. That's true for any subspace, right? You just have a basis for your space. Any vector in your space can be written as a linear combination of the basis vectors for your space. However, because the transformation is linear, applying the transformation to both sides, we get that T of X is equal to this linear combination of vectors, each vector being T of H sub I. But this linear combination has the same exact weights that the linear combination for X had. Now, because X is arbitrary and T of X is the image of that arbitrary vector under the transformation T, any vector in T of H can be represented as a linear combination of these vectors, T of H sub 1, T of H sub 2, all the way to T of H sub P. That is, the transformations of the basis vectors from H span T of H. Now remember, these vectors here will build T of H, but some of them might be linear combinations of others. So at max, the dimension of the space, T of H, is going to be the number of vectors you see there, which is P. And P, remember, was the dimension of H. We're not saying that all of these images are linearly independent. What we're saying is that if they were, the dimension of T of H would be P. But just in case, if they're not a linearly independent set, then we have to throw out one or two of them, or 3 or 4 or 10, who knows. And so the dimension will be less than P. But now we have proven that the dimension of the transformation space is less than or equal to the dimension of the original space. And that concludes that proof. It's a pretty robust proof, honestly, for an example and not a theorem, but it's definitely worthwhile to spend some time thinking about that. And by the way, every single one of these examples you run into in a linear algebra text is actually a little theorem that you're proving that might be useful later on. For example, if I run into any transformation between two finite dimensional vector spaces from this point forward, and if I know that maybe a subspace of the vector space V has dimension, let's say 5, then I know the transformation of all vectors within that subspace creates a subspace that has dimension at most 5. It could be actually less, but it won't grow. It'll actually stay the same or shrink in dimension. I completely understand that there wasn't a lot in this video, just a single theorem and an example. However, sometimes it's nice just to have a smallish video. Anyhow, have a great day and be a wonderful human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.